Hello and welcome to another video. In this video we're going to be working on minimize maximum products distributed to any store. And in this one you have an integer n indicating there's n stores, and you have m product types given in quantities. And any store can hold as many products as you want, but you have to have one type of product per store. And you want to return the maximum or the minimum the maximum of all of your stores the way you distribute your items in. So I'll kind of explain that a little bit better going through these examples. Essentially, this is like product type 1, this is product type 2, and we have 6 stores. And so the best thing to do is take this product type 1 and distribute it like this, where we have 2, 3, 3, 3, and this is 11. So this is 4 stores, and then this is 2 more stores. So we can't like say like let's just take some from here and some from here and put it into one store. We have to have one product in each store. So basically the first store would have 2 product 1s, then 3 product 1s, and 3 product 1s, and 3 product 1s, then 3 product 2s, and 3 product 2s. And you want to return the maximum of all of the values in each of your stores, which is 3 in this case. So here, the best way to distribute is 5 at a time. So you could split this one up into 3 stores, this into 2 stores, this into 2 stores, and you get 7 stores total. And then here, you only have 1 store, so you basically have to put all this into the same store. And they guarantee that there's more stores than like these number of items, so you can never have like 5 number of items and only 2 stores, right? Because then you wouldn't have a solution there. But yeah, so essentially how do you do this one? And this one is a really common pattern, I feel like. It's basically, it's similar to a lot of other problems like the cocoa eating bananas or maximum time to ship packages or something like that. And it's basically, we can just say like, we don't know the best answer, but if we say the max capacity, we can determine like what's the max capacity of a store, and we can just give it some number. And if we know that that number works, then we know that everything greater will also work. And then all we have to do is just check, do smaller numbers work? Because if I have the max capacity of a store and like a number line, right? If I just have some line, I guess I don't have a line here, but let's say I did. Let's say for this store, it worked. Then you know for all of this it'll work too. And for all of this, you don't know. So if for this it works, we can basically eliminate all this because we want the smallest max capacity. And now if for this it doesn't work, then we know for sure it doesn't work here either. And then we just check this section. So this is like a really simple binary search. So we can basically just figure out like what do we use for our bounds, and then like what's the biggest capacity or the smallest capacity that we're able to do this. And then splitting up the numbers is really easy as well. So let's say we have this like 15, 10, 10. We can just say like, well, if the max capacity of a store is like 6, all we have to do is just every single number divide by 6 and ceiling divide. So 15 ceiling divide by 6 would be 3 stores. 10 ceiling divided by 6 would be 2 stores. 10 ceiling divided by 6 would be 2 stores. So this takes 7 stores total. And then we just check like how many stores do we have and how many stores do we take, and do we have enough stores? And if it takes less stores than this, then it's always possible, right? Like let's say this took 5 stores and we have 7. Well, then it's always going to be possible to do this because we can just take something and distribute it somewhere else, right? Like if we have 5 stores with 6 items each, right? It's always going to be possible to distribute it to more stores. But if it takes 5 stores to do this and we only have 4, then we can't. So we basically just compare how many stores does it take and how many stores do we have. And the number of stores that it takes needs to be greater than or equal to the number of stores that we have. And then it's just like a basic binary search from there. So that's all we have to do is we can just make this helper function, like given a max capacity of a store, can we do this with n stores or less? And then we just binary search and return the best thing. Then I'll show you kind of like I think I showed this before, like a binary search template that I really, really like. You can use it for any type of problem. It's just very nice and you don't get a lot of errors. So first, let's just do this like can we split or something function. So you could say like private, and maybe a boolean, can split or something like this. And this will be like max capacity of a store. And we also need to pass in n and quantities. Okay, so essentially we just take every single number in quantities, then like I said, divide by the max capacity and just add it all together. So we can just say like int result equals 0. And for int q in quantities, we'll just do result equals ceiling divide of q over the max capacity. So if it perfectly divides, it will give you that exact number, and if there's a remainder, it will add 1, which is what we want. Then we just return, is the result less than or equal to n? And if it is, then there's a way to do this. So now in our binary search, all we have to do is use this, and then what's going to be like our upper and lower? So for the lower, we can just say like, doesn't really matter too much. We can just say like maybe the min will be 1. With 0 it won't work, right? So maybe the min's 1. And then the right can be like the maximum number in quantities. You could honestly, like you don't even really have to do that. You can just make it really big because binary search is really fast. But yeah, we can make the maximum number in quantities. So let's just do that. So we'll just like go through the quantities. And let's just be, so there we go. Okay, so now we just have the basic binary search template. So the way I like to do this is we're going to check for something, and then anytime it works, we're going to set our result equal to that, and then keep looking for something smaller. So we can just set a result equal to like int max or something, or in this case, we can just set it equal to right. Like if we set it to the max quantity, that will always work, because then basically every store will have one type of item, and it can have enough to just take that one type of item and put it in one store. So we can set it to this, and we can minimize later. And then you can use this. I always have it left is less than or equal to right. I don't like this one very much because there's like other things you have to do. I think this one's a lot simpler. So we'll get a pivot. And because you can get overflow, it's better to do this way. So this is basically an automatic ceiling divide because this is integers. And then we just check. So if can split, so this max capacity is going to be the pivot, n and quantities. So if this is possible, we're going to set our result equal to this pivot, and then we're just going to do the binary search. So we'll say result equals pivot, and we want to look for smaller values than this, so we'll just say this. Otherwise, so this is too small, so we'll make it bigger. And finally, we can return the result. So I really like this. It's very clean. You can use this for everything. And if you're comparing items to their neighbors, then usually I just compare the second to last and the second item to the neighbors first. And then I just run this binary search for the entire array, not including those two, and then this will work as well. I think it's a lot cleaner than memorizing, like, I know in the LeetCode there's examples like this, and it just gets kind of messy. So I think I like this a lot more. Kind of consistent, works for everything with a few modifications. Yeah. And so we should be able to run this. And so the basic idea is if we get a match, then we'll just try numbers that are smaller. And if we don't get a match, we'll try numbers that are bigger. And yeah. And then, if you have a no solution here, you can just make result equal to -1 or whatever it is you need to return if there's nothing. And then if this never hits, it'll basically just return -1. In our case, we know it's always possible, so we can make it right. But technically, you can make this number whatever you want. Like, we can make it, literally anything. It doesn't matter. Because we're always going to find something, we can do this if we wanted to. Yeah. So let's see what happens. Okay, apparently not. Yeah. Let's see if it actually did matter. I'm kind of curious. No, yeah, that's what I figured. I don't think it matters. Okay, so let's see what we did wrong. All right, so we got 4. So we definitely can't split it into 4, right? Yeah. So 4 doesn't work here, so this is too small. And this is screwed up. So I think it's just our can split function that's screwed up. Okay, so actually the problem here is, yeah, so in other languages, if you use ceiling here, this will work. But because this is an int and this is an int, this will already round to begin with. So we can do it another way. We can just say capacity plus, and then we can just have a ternary here. So we can just say Q mod max capacity is 0. So if it's 0, we'll add nothing. Otherwise, we'll add 1. We can do it this way. You could also convert them to doubles. I think this will be fine. All right, there you go. So forgot about that in Java. Yeah, because I was kind of using this trick here that basically when you do this, this is already a floor divide. So you got to be careful here, I guess, that yeah, you're doing a ceiling of a double divide, not a integer. But yeah, regardless. So this does work, and so time and all that, and yeah, basically this is like a common pattern where like it'll tell you like what's the shortest amount of time you can do something, or what's the minimum capacity you can have to do something, or any of these, and you can just recognize it's like this linear thing where it's going to be like fail, 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 and then at some point it will succeed, and then from there on in it succeeds. And then you can just binary search over that time interval. And usually that works for very big values, like you can do log 10 to the 9th, it's pretty small, and so on. But in this case, so essentially we're doing binary search up to the biggest item in quantities. So this will be like max quantities. And then for each one of those, we're iterating through the array. So this is going to be like log max quantities times n. I guess maybe you can write it like this if you want to. Something like that. And then here, so integer, 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 we don't have anything else. So yeah, we do have like a function, but that doesn't matter. So that's, and yeah, definitely a pretty common problem. I think if your goal is like to do well in interviews and all that stuff, I think this one should be very doable. Surprised this rate is honestly this low. I thought it would be like 70, but yeah, pretty standard binary search problem. But if you haven't seen this kind of pattern, kind of hard to recognize, because usually you're given like a sorted array or something. So it's kind of hard to think of like, oh, I can binary search through times or capacities or something like that when I'm not given that as an actual number. But once you see this, then you can easily apply it to a bunch of other problems. So hopefully this is helpful. If it was, please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.